So welcome to Hands-on Network Science. Let's start with what is a network? A network is a set of defined relationships across items within a set. There are a lot of different networks that can exist. For instance, we can have people connected to each other on social media. We can have geographic areas connected by animal migration patterns. We can even have stocks connected by buyer behavior or goods connected by a supply chain. And we can even have ideas or parts of speech connected semantically. There are lots of different networks out there, and most data can be represented as a network. There are a couple important structures that networks have that are really interesting for us to analyze and important to the overall functioning of the network. Hubs are densely connected regions. So we can think of groups of friends who all know each other or all frequent the same locations. We can think of cities that have many international flights connecting them to other cities, or watering holes where many animals congregate. Hubs generally are very dense, and there are regions where there can be a lot of very quick spread of ideas or diseases or behaviors. Bridges, by contrast, may not be densely connected regions, but they're connections between different regions. So an individual may span many different social groups and connect those groups together. Manufacturers may provide common parts that are used in a lot of different industries to tie together a supply chain. And common food sources might exist for many types of animals, such as bait balls in the ocean. There are many advantages of using network science formulations for data science and machine learning problems. For one, network science algorithms tend to be more computationally feasible than traditional approaches. For instance, let's consider spatial regression for change point detection across time and space. A lot of the traditional regression models have many autocorrelation components for both the time series part and the geographical part. This requires a lot of parameter fitting and large amounts of data to be able to get a good model, and a lot of computational time to estimate all of the parameters. However, formulating this as a network science problem allows us to scale a lot more quickly. And because the network can be distributed, we can actually parse this into parallel computing frameworks. The same holds for time series methods. A lot of models require a lot of assumptions, and they require a lot of parameter fitting and a lot of data to be able to fit an accurate model versus network science methods that can detect some of these changes within a time series very quickly and easily without a lot of parameter fitting. In addition, networks allow for a very nice visual representation of data and algorithms, as well as what's going on within the algorithms. So when we're looking step by step at how a network is changing or how different structures or spread are going on within a network, we can visualize each of these steps as output to be able to see how things are being fit over time. In addition, network science shares many deep connections to mathematics, including topology, geometry, and dynamic systems theory. And this allows us to leverage a lot of different tools to understand what's going on in the network and be able to come up with new algorithms that we can run for specific purposes. Let's dive into a couple of case studies and see network science in action. Our first case is one of the more typical uses of network science, epidemic spread. So in a lot of communities and social networks and other entities involving people, we often want to predict and stop disease, harmful behaviors, or other things that are going on within this network to be able to protect the health of the population. And as we can see on the right, there's an example of a social network, my own social network back in medical school. And we wanted to look at specific tools to be able to identify spreading behavior on a network like this. So first, we collected this data set, which is static. It's not changing over time. And it represents friendships across two different social groups that are just connected by two individuals. And we wanted to look at disease spread to predict severity within the network and test out different strategies to be able to prevent disease spread within the network. So we looked at, first of all, different SIR models, which model different parts of the epidemic. You have susceptible populations that haven't been infected yet, infected populations that have the disease, and recovered populations that have already had the infection and are now immune. And this model is a system of differential equations that can be adapted to the connectivity of the network so that we can look not just how it might spread through a population, but how it would spread through a population with specific relationships in place and specific hubs and specific bridges. On the upper right, it may be a little bit hard to see, but we can see the epidemic on the full network with one of the types of epidemics that we wanted to run. There are different parameters that we can play with within the differential equations that will control the spread across time and across space. So this involves an epidemic that crosses 4 different time periods and infects most of the individuals in the network. However, we wanted to look at specific vertices in our network that we could remove. Within a real epidemic, we might quarantine the individuals or vaccinate the individuals to prevent them from being able to spread a disease within a hub or across bridges that connect different hubs. And we used a tool called Foreman-Ricci curvature, which is a geometric measurement of centrality. Essentially, it measures how much other vertices are tugging at a specific vertex to create a force of attraction on it. And so we removed the highest ranked vertex, and we found that we lessened the epidemic by 1 time period, and there were a lot fewer individuals being infected. This was about half of the network that was infected versus the entire network. So we found this to be one of the more effective means of controlling the spread of disease within a network. And in other papers that have come out, they found very similar things in different types of epidemics and different types of behavior spread. Just removing 1 or 2 individuals from a network through vaccination or other targeted public health campaigns, these epidemics are able to be stopped pretty quickly. Let's switch gears and look at a different problem, the problem of stock market prediction. So one of the big problems within investing is market crashes. It's very important to understand when these might be coming to be able to put economic policies in place to soften the landing for those impacted, to be able to adapt trading behavior and strategies for upcoming crashes and downturns in the economy. So this is a change point problem in time series analytics. However, the data is often not stationary, which is an assumption of a lot of common parametric time series models. And it's also difficult to model time series data at scale. So if we're looking at daily data over decades, it can be very difficult to fit these models computationally. So we decided to look at a network science way of predicting these crashes. So we collected NASDAQ data from 2004 to 2020 for 4 different stocks, Apple, Alphabet, NVIDIA, and Microsoft. And when we looked at this, we see different periods where there's growth, there's crashes, there's acceleration of growth, and these don't always overlap. So we can see here in 2014 and 2015, we have Apple kind of making gains while the others are fairly constant, and Alphabet kind of had a downturn in that period. So while some of the behavior is fairly correlated, we don't see that across all of this. So we wanted to see if we could predict the volatility of the stock market using our Foreman-Ritchie curvature. So for this, we windowed our time series. It's a pretty common technique within time series to kind of partition out the series into time windows. And then we created thresholded correlation networks. So we looked at the correlation across stocks within that overlapping time window for each of these windows, thresholded them. We looked at a couple different thresholds of correlation for what was correlated and what wasn't correlated to create a network. And then we tested a few different network science tools to see which ones were good at predicting future volatility of the market. This included Foreman-Ritchie curvature again, betweenness centrality, PageRank centrality, and degree centrality to assess this risk. And we found that most of them do a pretty good job of figuring out where the correlation is happening and where things are getting to be more coupled and more vulnerable to outside effects that might tip many stocks at the same time. And we can see the results on the right. The spikes in these different colors indicate periods where volatility is increasing. And we did find the periods where we would expect to see this change, including the crash of 2008 and the effects of COVID. Another important problem is understanding the impacts on food pricing across different geographies. There are a lot of local and global factors that can influence local prices of goods, and being able to understand when those prices might spike is really important for food security. So within this, we wanted to look at millet prices across markets across the country of Burkina Faso, which in this time period were impacted by supply chain problems, global trends such as COVID-19, the war in Ukraine, and also local variations in rainfall, in temperature, which all have an impact on the local supply at markets. One of the cool things that we can do with this is look at climate change over time, how local factors are influencing certain markets and where food aid might need to go within a geographic region. So this data set has spatiotemporal aspects. It has both the spatial component across different provinces of Burkina Faso, as well as temporal effects of collecting this data over time. And spatiotemporal regression models have a pretty high computational cost and require a lot of assumptions of stationarity, which our data did not meet. So we turned to network science to try to find some of these change points like we did with the stock market, just within the context of spatiotemporal data. So we had quarterly millet prices that were averaged across each region. The time period was from 2015 to 2022 across 45 administrative provinces, with market prices for each province averaged for that time period. We looked at overlapping time windows again, and instead of using correlation, we used a spatial data statistic known as the local Moran statistic, which essentially does a geography-based twist on correlation. We were looking at correlation that was weighted spatially with provinces that shared a border. And for this, we limited ourselves to looking at PageRank centrality and Foreman-Ritchie curvature centrality to assess the risk. We plotted one of our time periods right here to see markets where prices were very correlated. As we can see, there are a lot of different fractions here. We have some that have very high correlation that form clusters of price and geography, and we have some that are fairly isolated and fairly weak correlations, which is very interesting. These patterns changed a lot over time, as we can see in the bottom right. We have Foreman-Ritchie curvature changing quite a bit over time. And we do see, as 2020 approached, that the volatility was increasing within prices. which essentially set up a bad event once COVID happened and some of these global impacts started. Fortunately, the volatility seems to have leveled out a bit more in recent times, which suggests that prices might stabilize in the future. In conclusion, there are a lot of benefits of network science-based approaches to data problems, including computational feasibility, easy visualizations, and interpretable results. Some of the future directions where we haven't seen a lot of work in network science include these spatiotemporal and temporal data applications. There are a few papers out right now, but it hasn't been widely explored with all of the different types of data and different types of tools that can be developed for change point detection and data mining within these frameworks. In addition, the scaling of problems is another direction to be explored, especially within some of these more novel uses for network science. There are a lot of different software packages that can be used, especially iGraph, NetworkX, and there are a lot of books out there that can be used. The one that our team collaborated on that's been released is The Shape of Data. And there are a lot of tutorials that you can find if you Google some of these network science tools and packages. So whether you're a Python user or an R user, you should be supported. And that's the end of our presentation, and we can skip to questions now. Do we have any questions?
Ce monde doux est dû principalement au réchauffement climatique, qui affecte violemment la région. Les températures élevées sont comme le feu, même à l'intérieur des tentes, et on n'a pas de ventilateur.
Okay, I can answer that. It has to do with the formula. You can change the sign and it becomes positive. But the way that it's measured, typically we're looking at negative values because it creates a hyperbolic space. Anything you want to add?
Yeah, I think is more or less what you said. So the curvature can be negative depending on the shape of the data. You know, when we are in geometry, if you consider, for example, a sphere or a plane or an hyperbolic plane, you have a negative curvature. And then when you have, for example, a sphere, the curvature is positive, and the plane, the curvature is negative. So that's why we're having this. Yeah, I hope this helps.
Yeah, just about every network winds up being a hyperbolic geometry. It's very interesting how that works. I think because there are so many spokes as opposed to dense hubs that it just kind of works out to be negative.
Okay. So is this we have Dennis who asked, can you talk more about what thresholding means? That's in the chat. That Dennis O'Brien in the chat.
Yeah, I can get us started on that. So thresholding is basically choosing a cutoff value above which a connection exists and below which a connection doesn't exist. There are weighted networks and unweighted networks. A lot of times it's advantageous to use the unweighted networks. A lot of the more complicated mathematics works out a lot nicer when we are just working with ones and zeros versus fractional values.
Yeah, I think that is enough. I think it's okay. Yeah.
Okay, it looks like another question. Is your book a good place to start for someone who doesn't have much experience with network analysis science? Yes, I would say so. We haven't assumed any prior knowledge of network science. The shape of data doesn't have any assumptions of that. The second book that we're working on focuses solely on network science and is a bit more advanced with the applications, but the shape of data keeps things pretty simple with social networks.
I think that's okay what Sarah just mentioned. I think it's okay. You can start in that book, and there's another one that's still in. We are building on. This is focused on network science, but if you want, I can give you some more interesting reference where you can start from basic network science. So I can type some links in the chat. Yeah, some nice reference, and then we can start from there. But I think the book of Farrelly is a nice place where you can get some insight on network science. Yeah, we just had 30 minutes, not a place to lay out all the network science background. Thank you. Let me
Any other questions while Frank is looking for the references? There are a lot of tutorials out there with Python in NetworkX and iGraph. Looks like here, is there any place we can see the notebooks and examples? Yes, that's something I can provide. I don't think we have enough time to go through all of the code for them. But if you want to connect on LinkedIn, I can send you the notebooks and the data for each of these. The first example you can find on the Shape of Data's website with No Starch Press. That's all open source code, and the others are from our forthcoming book. So that is my contact if you want the notebooks that are not out there yet. I can send those to you.
So, any other question? I think I just sent a link on the book entitled, I think, Structure of Complex Network, Theory and Applications. Yeah, that one I think is important. Yeah, it starts from basic stuff to more advanced stuff. So they have theory and application, so it can give you idea. And yeah, as I already mentioned, I think a good way to start when you want to code is Python, and you can look at iGraph and NetworkX. I think they are on the slide, and then they are very nice tutorial. And also in the book of Farrelly, the first one, the shape of data, you have also very nice code.